If I have an autonomous differential equation of the form dx dt equals f of x, the equilibria are the points where dx dt is equal to 0, i.e., where f of x equals 0. If f of some number, x sub e, let's call it, is equal to 0, then x of t, being constantly equal to that number, x sub e, is a solution. This constant solution is an equilibrium. And it's a solution because d dt of a constant is 0, and f of that constant is also 0. This means if we have the initial condition that x of some time, let's call it 0, is equal to x sub e, then the solution must be x of t equals x sub e. If we start at the equilibrium, we stay there for all time. This is just the definition of an equilibrium. But what if we have a different initial condition? What if we have the initial condition x at time 0 is some number, x naught, that is close to x sub e, but not exactly equal to the equilibrium xe. Then what happens? Well, there are different possibilities. Maybe x of t moves away from the equilibrium as t increases. Or maybe x of t moves toward the equilibrium. And we'll include in the second possibility that it at least doesn't get any further away, it just stays the same distance away. In this first case, we say that the equilibrium is unstable. For an unstable equilibrium, if the initial condition is exactly at the equilibrium, we'll stay there, by the definition. But if we start just a little bit away, as time increases, we'll move away from the equilibrium. This is like the idea of balancing a ball on the top of a hill. If the ball is exactly at the top, it'll stay there. But if it jiggles a little bit one way or the other, it's going to go down one side or the other, depending on which way it jiggled. In the second case, when x of t moves toward the equilibrium, we say the equilibrium is stable. The stable equilibrium corresponds to the case where a ball is sitting at the bottom of a valley. If the ball starts exactly at the bottom of the valley, it won't move. But if it starts a little bit away from the bottom, it'll move back toward the bottom. So the ball moves back toward the equilibrium. So when we find an equilibrium, we have two cases. The equilibrium might be unstable, or it might be stable. And one important goal when studying dynamical systems, such as this differential equation, is to find methods to determine the stability of the equilibria. In summary, for our differential equation dx dt equals f of x, the equilibria are the points x sub e, where f of xe equals 0, which means dx dt is 0, and the solution x of t is x sub e for all times. Equilibria can be either unstable or stable. They're unstable if nearby trajectories, or solutions, move away, and stable if nearby trajectories move closer, or at least don't move further away. The next question is how to determine stability. Let's start off by thinking about the graphical approach of solving differential equations. In the graphical approach, we plot f of x. Let's say it looks something like this. And we use this plot of the function f to determine what plots of x versus t might look like. One important point to remember is that these two graphs are very different. In the plot of f at the left, x is on the horizontal axis, while on the right plot, x is on the vertical axis. The equilibria are points where f of xe equals 0. So we can find them by looking at the points where f intersects the x-axis. In this case, we have three equilibria. We can also plot those three equilibria on the right figure. The one where x is largest would be somewhere around here. And the second one, x is just below 0, right around here. And the third one, x is even more negative. On the left plot, it makes sense to draw these equilibria as points, because these are the values of x where f is 0. On the right plot, though, we're plotting versus time, and the idea of an equilibrium is that x of t is at the value x of e, the equilibrium value, for all time. So if we were to plot an equilibrium versus time, it should be a horizontal line, or the plot of a constant function. So this largest equilibrium would be a line like this, the middle equilibrium would be a line like this, and the smallest like that. The stability of an equilibrium captures what happens to solutions that start nearby the equilibrium. Let's look at this upper equilibrium first. If I start just above the equilibrium, the question is, do I move toward or away from the equilibrium? Well, looking at my differential equation, dx dt equals f of x, I can see that to determine the velocity dx dt, I just need to look up what f of x is. Well, for this value of x, f is negative, so that means I must move to the left. So if I start over here to the right, I should move with time toward the equilibrium. If I were to plot this versus time on the right, I would start up here, and as time evolves, I should get closer to the equilibrium. What happens if I start just below? Then when I look up my velocity, I see that dx dt, or f of x, is positive, so I should be moving toward the right. So if I start down here below, I should move up and get closer to the equilibrium from below. On the plot versus time, it looks something like this. So for the upward equilibrium, nearby trajectories are moving closer. So therefore, the upper equilibrium is stable. How about for the middle equilibrium? If I start at a value just above the middle equilibrium, the velocity, f of x, or dx dt, is positive, so I should be moving to the right. So if I start over here, I should move on toward the right. In fact, no matter how close I start to the equilibrium, f just above the equilibrium will be positive, so again I'll be moving to the right. If I plot that result on the figure at the right, if I start here close to the equilibrium, I'm going to move away. And in fact, in this case, I'll move to the upper equilibrium, but that doesn't matter as far as the stability for the middle equilibrium is concerned. Stability is just a local behavior, what happens when you're nearby an equilibrium. On the other hand, if I start just below the equilibrium, the velocity f of x, or dx dt, is negative, so I'm moving to the left, no matter how close I start to the equilibrium. Plotting this versus time, I move away from the middle equilibrium. Nearby trajectories are moving away, so therefore this middle equilibrium is unstable. What about the lower equilibrium? Well, I already saw that if I start above, I'll move closer to it. And in particular, if I start very close and above, I'll move closer to it, since the nearby trajectories are the important ones for stability. So if I start here right above it, I'll move with time closer to it. And if I start below, f of x is positive, so dx dt is positive, and we move to the right and get closer to the equilibrium with time. The plot with time looks like this. Just as for the upper equilibrium, nearby trajectories move closer, and the lower equilibrium is stable. Just by looking at the graph of the function f of x, we can determine the stability of the equilibria of dx dt equals f of x. We can also determine the stability analytically, which will be the subject of the next video.